Thank you for having me here, and thank you to the organizing committee for planning it so well. So it's not my first time to Nepal. I have been here many times, and my sister-in-law is also from Kathmandu, so I'm quite used to this place. But this is first time for me to be the part of this school, so I'm really looking forward to it. Do we have some change? Slide changing? Primarily talking about graph machine learning, and I came to know that we have a very diverse set of participants, mainly from undergraduate background. So I will try to keep as a bit light in terms of the depth. We will be trying to cover many topics in the line, and if you need to know more detail, I am here. I will be happy to. Just a second. Fine. So I will be talking about graph machine learning. We'll give some basic setup of what it is, right? And we'll talk about core challenges that we are facing now in terms of extending the next frontier of machine learning, right? So let's start with a graph as a universal data structure. It's very simple. You need to have set of nodes and set of edges. Nodes could be anything, and edges are primarily representing the relationship between those nodes. So the examples are quite wide: traffic graphs, social network graph, brain graph, economic activity graph, molecules graph, precipitation graph, circuit graph, and image. These all are some of the examples of graph datasets. So you can say graph datasets are quite ubiquitous and quite universal. So if you can pose your problem as a graph problem, you should do it. There are some caveats of it that we will be talking about. Why so? Because with graph based representation, you have extra information about the relational structure that you have, and those in many times are quite powerful. In fact, for many of the semi supervised learning and self supervised learning, graph based representation is the first way to represent the problem. Why I'm talking about graph? So there are some papers, recent papers from Nature portfolios about using of graph in several domains. So we can see the diversity of the application are quite huge, from the understanding of ammonia oxidation to understanding of urban networks to understanding of protein ligament affinities to molecular contrastive learning. So all set of very diverse domains are primarily captured and can be captured and can be solved by using graph based representation. There was also a recent primal on Nature about the utility of graph based modeling for the next frontier of drug discovery. Why graph so important and why graph is so universal? So there are many ways to explain it. Some of the ways are primarily, you can see different data sets, different type of data have their own shapes, right? And if you really want to model something quite well, you need to understand the space and the shape of the data, right? So far, if you have enough amount of data, you will not face this issue. That what we have been doing for the internet scale problems. Just have as much amount of data sets that you can have and model it, right? Like LLMs and all are primarily data hungry things. But many of the domains data sets are the gold. You cannot have too many examples. For example, in healthcare, if you really want to study cancer, you cannot have million patients having cancer profiling done. So number of data sets are quite less. So the moment you have the issue of less number of data sets available, less number of labeled data sets available, you don't have the luxury of or maybe you need to do something where you can understand the data well. And how do you understand the data well? Understand the space of the data, what is the space of the data, and understand the characteristics of the data. So data has shapes, and graph-based modeling helps you to approximate that shape. On a side note, many of the physical processes like Laplace equation, heat equation, wave equation, Poisson equation, many different equations you from a different disciplines you might have encountered, they all can be explained by Laplacian operator, Laplacian Beltrami operator, right? And Laplacian Beltrami operator for the graph domain, the discrete approximation of it is a graph Laplacian matrix, which is quite regular and quite frequently used to represent and study graphs. So far we have quite well motivated the usage of graph. And graph based ML is not new, it's quite old, it's quite primordial, and the contributions in this domain have come from across many disciplines, from physics, from statistical mechanics to electrical engineer to computer science engineers. Different disciplines have studied the phenomena of graph based representation for their domain in different contexts. Right? So if we just try to restrict our attention to the ML part, earlier we represent a graph, okay? I think I am talking about around 90s work. There were two methods to deal with, use graph. One was a level propagation. The extension of it was what we are using now in terms of the message passing and also level propagation, and another was a regularization based method. In level propagation, what you do, you have a data set, you learn a graph, and then you ask your neighbors what are their levels, and then keep doing it till the time you are satisfied. So whatever your majority of neighbors are, you become the same. Right? So level propagation was quite used earlier. The only thing now change is the wrapper that we are using currently are of a neural network. Okay? So it's not new, it's quite old. This is one of the explanation of why it makes sense. So in the right you see this is in this case, if this is the shape of the data, right, and you want to study it, one of the major things what we do very frequently is to understand what are the neighborhood structure of the data, right. So if you will really, for this kind of a data set, this is not working, right, it seems. Okay. So for the neighborhood structure, if we will compute the distance between these 2 points, and if we will only use so-called known as the Euclidean distance directly, the distances would be this, but this point is not the neighborhood. So in order to understand the shape, you need to understand the curvature of this. One of the way to do is that you approximate the neighborhood graph, and whatever the graph distance is, that becomes your distance. So just a very high level example of how graph based representation is also helping you to understand the shape of the data. Okay, so yeah, so the problems earlier was level propagation, just build a graph and propagate the label, and next was a regularization based method. So whatever problem you were solving earlier, this was your older loss function, and now you have a graph information, you use it as a regularizer and solve a new problem. So these were the two old existing methods to use graph in your approach. Now with the deep learning paradigm, you have neural networks, you do message passing. I think you know all these things from the previous lectures, and you solve problems like node level problem, edge level problem, and graph level problem. So I'm not going to talk about these architectures. My motivation for today's lecture is something different. So we want to make our ML system trustworthy, right? When can something become trustworthy? Can someone answer this question? When you start having trust in a particular system. So what is your sense of trustworthiness? Reliability. Yes, reliability also. Transparency, yes. And what do you mean by transparency? When you know about? You know about the system. So in a sense, you are able to explain why the system behaved in this manner. That is the meaning of transparency, right? And someone also said explainability, right? Yeah, so these all are the facets, the core facets of the meaning of, or when can we say something is trustworthy. So if you really want to articulate and quantify, if you are able to handle massive size, right, you are not biased, your models are not biased, your models are fair, and at the end your models are ethical. If you have all these things taken care, then your system becomes fair, right? So now primarily from the ML community, right, there is a strong amount of thrust in making things reliable. So in terms of algorithms, we have quite reached good amount of maturity for many of the problems, right? We are doing quite good. But now, do we have trust in that model such that we start using it for publics, right? For in different applications. So from the algorithmic perspective, someone told me that if you how as a person we gain respect, right? So if you only do what you are supposed to do, you will be valued, you will not gain respect, right? But if you are able to do more than what you are supposed to do, then you will gain respect. So something similar also ML framework have to be doing. ML tasks are there, ML models are there to help you, but it should not only solving a problem, it should also ensure certain level of reliability, right? Such that if I am using this model, I should have the whole understanding of why it is doing so. I should have the confirmation that it is not biased, right? All these things need to be taken care of. So for our case, what we will be taking care of, how to take care of one of the core issues of graph thing, the massive size. In a sense, when you grow, the size of the problem grows, how you can scale that problem, and we will be talking about how to make models fair. Okay? Just to for a touching note, when we want to have ethics in AI, and ethics in AI operates at all three layers. We have three different phases of AI. First phase is what? Data collection. You plan a problem, then you collect data. In many cases, the data sets are already available to you, but in many other cases, you plan experiments and then you collect the data, right? Collecting data, that is the first phase. Second phase is optimizing it, and third phase is deployment. Trustworthiness needs to be ensured at all these three layers. If any of the one layer would be missed out, then the overall scale of inequality will be scaled up. It will not be optimal, right? Why you think so? In terms of the optimization part, you see what you collect data is your memory, right? Data is the feed to your model. So whatever your data would be, your model would be learning based on your data. That is fine. That is now where we will not be focusing. Next thing, the training part. So what you optimize, you become, right? So for us who design AI ML algorithms, our contribution primarily are limited to the second layer. First part is where data set is coming, where the domain expert will come. Third part is the deployment. Once you develop the model, you make it public. Whether you make it public or whether you charge it, that is the part of a deployment thing. But for us, we will be primarily dealing with the training part of it for the most of the ML engineers who would be building models, right? So we need to be understanding and trying to understand what kind of training paradigm we should be building, whether just the MSE loss function is sufficient or something else we need to bring in, such that we should be optimizing which is better, right? So throughout the talk, I will be touching upon these things slowly. Let's see, and feel free to ask questions in between also. So firstly, I will be talking about this issue, right? So when I represent the problem of my ML problem as a graph problem, of course, I have extra informations, right? Not only I am dealing with node features directly, I also have the connectivity information. But what I am bringing in further is that with connectivity, I have a different matrix to take care of, which is the connectivity matrix. So earlier, if my data set was only n cross d, now I have to deal with n cross d matrix and also n square matrix of the connectivity information. So, so of course, we are having extra information, but to deal with these amount of informations are quite difficult to process, right? So in regular ML also, or in the Euclidean space also, you must have heard of dimensionality reduction. How many dimensionality reduction techniques you are aware of? Just name a few. PCA, something else? Low rank matrix factorization. These all are some of the examples of dimensionality reduction. But do we have something for graph data? Or can we directly utilize existing dimensionality reduction techniques for graph data? Any answer? No? Yes? Why we cannot apply existing or Euclidean space dimensionality reduction techniques for graph data? So with graph, what you have, let me give you one example. Okay, so I will talk about. So first phase would be to deal with it. I will talk in great detail. Next phase would be to deal with this problem. Okay, if my model ideally should be trained and tested on clean data, but in practice we do not have always the availability of clean data. We have noisy data. Sometimes noisy data sets are the part of a nature, and also sometimes it's adversarial. So can we make our graph neural network model robust against adversarial attacks? This will be the second theme of the discussion. So primarily we will be talking about these two themes, and third theme would be on the fairness part, right? Okay. So let me start the idea of, or start the first topic of graph coarsening and the graph reduction. Okay. Okay. See. So existing graph sizes are increasing day by day, really massive. These are the existing techniques like sparsity methods, matrix factorization, low rank approximation, subspace methods, PCAs. These all are primarily for the Euclidean case. This will not work for our graph data, graph based data. Why so? See, what do we have? It's a very toy example. What is the meaning of graph coarsening? You have graph, earlier you were just having features, but now what you have, with features you also have the connectivity information. So you need to deal with the reduction part, not only on the features, but also the matrix that represents the connectivity. Okay? That makes this problem whole complex. Earlier work deals with sparsification. What is the meaning of sparsification? You have a graph, suppose n number of nodes are there, and e number of edges are there. You somehow remove the number of edges. So earlier, if e number of edges are there, after sparsification, you will have maybe e by 10 or a much reduced number of edges. This is also fine, but it does not reduce the number of nodes. Still workable, still having very good guarantees, and have contribution with very well defined, you can say, theoretical guarantees. But what we want to focus is on this kind of a paradigm, where I just do not only reduce the number of edges, I also reduce the number of nodes. Okay? So just think here, with this each are the nodes. Nodes could be person, anything, right? With each node you have features, and from this I need to aggregate a set of nodes together. And what we need to look here, those set of nodes which are redundant. Redundant means having similar information, compress it and learn a new structure. So this is our current focus, and this is known as graph coarsening. The moment you are able to do it, right, suddenly what you would be able to do, whatever you wanted to do on 1 million size graph, just for example, you could do exactly same thing with much reduced size graph. How it will ensure trustworthiness? One of the biggest issue currently is of what? The compute power, right? The industry is leading that race because they have enough resources. The moment you are able to compress the data meaningfully to a massive scale, then suddenly you are allowing low compute resource player also to participate in that race. First. Next thing, the moment you have reduced size of the data, and this can be applied to models also. We will also talk about models, how to reduce the size of a model, but currently we are talking about the data. If you have a reduced size data, meaningfully reduced size of the data, then it can also be put on edge devices. Okay. And third part, which is also related to privacy, is that suppose some of the attributes here are sensitive, right? And you wanted to conceal it for sharing, right? Sharing these days has also become issue, right? You cannot share your data set among different partners to collaborate also. The issue is that your sensitive attributes will be revealed. But if you are able to do coarsening and also guarantee that the sensitive attributes are concealed, then you are also allowing what? Privacy preserving mechanism, right? So 3 layers. First layer is that you are suddenly able to scale up the problem, right? You will be allowing for the edge devices to do the same amount of tasks which ideally require massive compute. And thirdly, you are also able to do privacy preserving, or you allow privacy preserving sharing of the data sets. So let's start to solve it, right? So coarsening is also a very, you can say it's a whole universe if you want to see, and it's very subjective, right? What we have focused on is to learn some structure like this, okay? Suppose I have a graph structure like this. We have 5 nodes, okay? What we want to do, we want to identify a set of nodes which are similar and want to put together, okay? So in this case, these 3 nodes were somehow similar. So I wanted to map 5 node graph to 3 node graph, okay? And this example here, I have merged these 3 put together in one. So at the end, what I need to learn? I need to learn a mapping from here to here. So the mapping would be known as the coarsening matrix. What is C here? C would be this times this size. So 5 times 3, and the columns would indicate what? Columns would indicate the number of nodes in this graph, and whatever entries are 1, it will simply indicate that. Now in this case, this is 1, 2, 3. So 1, 2, 3 are mapped to node 1, 4 is mapped to node 2, and 5 is mapped to node 3. Right? In a simple case, coarsening would rely on identifying a kind of a mapping matrix. But the catch here is, do you think this problem is easy? Given a graph, large graph, I want to learn a small graph. What could be the challenges that you can face here? That is true. Loss of information will always be there. But something else. How you will do it? So for this graph from 5 to 3, how many, for the given graph, how many coarsened graphs are possible? Many, right? For this example, for this particular mapping, this is C, but these 2 also can be put together in one. These 2 could be put together. There could be different combinations. So exponentially large number of combinations are possible. So you need to articulate it well, right? You need to come with it's not a random thing that you can do. You cannot try too many coarsening metrics, and there are too many coarsening possibilities, right? So you need to have some kind of a principal mechanism to deal with it. Okay. Okay, just to represent the problem setting and the notation, what would be given to you? The given to you would be this graph. We will represent this graph through the Laplacian matrix. I assume you know what is Laplacian matrix. So for now, this is just theta. What I want to learn, the mapping C. So the Laplacian matrix of this, which is theta, and Laplacian matrix of this, which is theta C, would be related in this manner. So if you know theta and C, you also know the matrix of that graph. Okay. So the relation between theta and theta C is this. What is C? Structure of C is what? C is a if this is n and this is k, so n cross k matrix with entries 1 or 0, and columns are orthogonal, right? Columns would be orthogonal. This is the setting. Okay. Let's come together. A very brief lookup of the work, whatever have been done so far in this area. Before, I think most of the work, very recently I guess from this work, all earlier works were not dealing with features. They were mostly dealing with the graph matrices, not features associated with the nodes. So you have a graph and compress it. Now what we want to do, we also have graph with each nodes there are features. Edges may also have features. And can you come up with a coarsening mechanism? There are recent works based on deep learning based work where they use both features and edges, both features and labels, but those are very much task dependent. So how they do, you have a large graph, you use that, you generate a small graph, you do a parallel training, match the gradient. Right? So it is also, they are also able to take care of the feature part in it, but the issue is that they are very much task dependent and may not be generalizable. What we want to come up with is a very optimization based routine which is task independent. So for any graph you come up with a method and that you can apply to any other any applications directly. Okay. Now just look at one thing. So we have a graph, we want to coarsen it, but coarsening is a NP-hard problem because the possibilities of coarsening matrix is too many. We want to now characterize that what we can do. So there is a kind of a graph data which is known as smooth graph or homophily graph. Have you heard of homophily graph? No? So homophily graph are those types of graph where if two nodes are connected, then their features are similar. So if you have form a bonding among yourself, then it means either you are sharing same hotels, right, or same cab frequently, or must be sharing same table during the lunch, breakfast, right. So if two nodes are connected, then they have similar features. Means if in that case the Euclidean distance between the features of nodes would be less and the corresponding weights would be higher. So we will restrict to the homophily type of a graph. All right. So what indication is, if you really want to do coarsening is a very less solved problem so far in our group. We have only taken care of homophily type of a graph. There are plenty of different types of graph structures and those are completely untouched. Graph compression is a very less explored problem, and whatever we will talking about all are the recent publications from 24 to 25. Okay. So how we define homophily mathematically? It is easy to say, okay, if I am connected to you, we have similar features, but how we define mathematically? So for suppose this graph, F1 is feature, F2 is feature, F3 is feature, F4 is feature, and L is a Laplacian matrix. So if I will compute this thing, F transpose LF, L is a Laplacian, then it will simply compute what? Weight into feature of I minus feature of j square. So it will sum up, suppose for a given graph, what I do, I compute the differences between the features, all possible pair of features, and sum it up. Okay. So if my graph is smooth, this value should be smaller or higher? Smaller, right? So now we have one measure, right? If I have a homophily graph, given graph, and if a homophily graph needs to be satisfying the property of smoothness, then the value of this matrix would be small. So we will be using this matrix. Just for example, the color is not very clear here, but the color what we are showing here, these are blue, 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 red, 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 blue, blue, red, red, right, mixed. So blue means similar feature, blue is one kind of a feature and red is another kind of a feature. So for this graph, there is only one disagreement somewhere here. The value of smoothness, this is also known as the Dirichlet energy. Dirichlet energy is 1, and for this case there is a lot of disagreement. The value of this is higher. So the takeaway message from here is we will be focusing on homophily graph. Homophily graph simply says that the input graph that we want to compress are homophily, means if they are connected, the features are similar, means the Dirichlet energy would be small. Now what I want to do, want to coarsen it. So while coarsening, one of the metric what I can use is what? The Dirichlet energy of the coarsened graph should be small. Okay. So just remember this metric, we'll come back again. Now, slide D2, just to contextualize what we have done and how we will be approaching this problem from an optimization framework. There is a thing called graph learning from data. What is graph learning from data? Graph learning from data simply means I have p number of observations, p number of you can say nodes, and corresponding to that I have n number of observations. So it's a p cross n dimensional data. I do not know the structure of the connectivity. So I do not know how x1 and x2 is connected to each other and with what weight. Okay. So to build this, the graph learning simply means that given just raw data, that is x, you need to come the connectivity information. Okay. So we approach this problem through different routines. One is a probabilistic routine also, probabilistic, so Gaussian Markov random fields are also example of this. In that case, the parameters of your distribution becomes the graph. And there is a physically inspired model also where smoothness becomes your part. So just for current context, if you will solve this problem where theta is Laplacian, trace of x transpose theta x is the Dirichlet part. So theta is not known, only x is known, okay? And theta is your graph. When you will solve this problem, right, then whatever theta you will get will be your graph matrix. Okay? So how we will be using it, we'll see soon. So this is what we propose. So just request your attention. I have this graph. With this graph, theta is my Laplacian matrix, and x is the feature of this. Feature means x1, x2, x3, x4, x5 put together. I want to learn a quotient graph. Fine. What I am proposing here, theta and x is given. What I want to learn, this theta c and c. Okay. Theta c and theta c should satisfy what? Theta c should be equal to c transpose theta c from the property of graph coarsening. And what are my features should be satisfying? See, x is of what? N cross d, for example, n number of nodes, d dimensional feature. C is what? N cross k. And x tilde is what? The reduced dimension. So the reduced dimension feature should be what? K cross d. So my features should be satisfying this. So now just look at this problem. Given theta c, given theta, when I will solve this problem, okay, we'll solve this problem, then just look at this. The first part is nothing but the graph learning problem from theta tilde. So what I am proposing here is that I will be coarsening this feature and learning graph on the quotient feature. I will be coarsening the feature, compressing the feature, and learning graph on the compressed feature. So what output I will get would be the reduced graph. Okay. If you are not able to follow the exact detail of it, then also it's fine. But what you need to motivate now from your side is that this is an optimization based routine. We have not assumed anything extra from the homophily assumption. So it can be applied to any domain. Wherever there is a need of graph coarsening, it can be applied to any domain. Okay. But is this problem solvable? No. Why this problem is not solvable? There is couple constraint here, right? Couple constraint is there. Whether the problem is convex or non-convex?
Convex.
Who says convex? It's convex? So how you think so?
The connectivity will be convex.
Connectivity?
Yes.
No, the problem is convex. Connectivity is an element, right? So connectivity cannot be either it's a convex set or convex function. So now what I'm talking about, whether the problem is convex optimization problem, it means whether the whole objective function is convex, the constraint set is convex set or not. So you are saying it is convex.
Yes.
So hint it is not convex. Why it is not convex? For many reasons. This part is convex for sure, but here both are variable, coupled, right? Because of this also it's not convex. Because of this constraint also it is not convex, and because of this constraint also this is not convex. So in general this is a non-convex problem, but non-convexity is not an issue. The issue is that the couple constraint here, dealing with it is quite difficult. Certain mathematical details, just a running commentary. Ki if this is a graph matrix theta which is connected, and C is how we have planned to learn, then this will also be a connected graph. There are some mathematical restrictions available that if the graph would not be connected, then the optimization problem will become non-solvable, and then that will create an issue. You may ignore it. Third, the first objective was convex with respect to C. But let's see how we will solve it, right? We'll try to cover it as soon as possible. So we have this optimization problem. This optimization problem simply, on a very high note, saying what? This constraint will force you to learn x tilde, and this will force you to learn the graph Laplacian on the quotient side. Okay. Dealing with these constraints are difficult, but this is a very easy thing. You can see, if you know C, you already know theta C. So knowing C is same as knowing theta C. So I can remove this constraint here and directly replace theta C with C transpose theta C. So first relation was natural. I will directly solve theta C with respect to C transpose theta C. So theta C as a variable would be removed. This is difficult to deal with because C is also a variable, right? And x tilde is also a variable. So what I will do, I will relax this constraint and move as a penalty. So I will relax this constraint, move as a penalty. And next, also to ensure the structured sparsity, I will use this regularization. So just for now, what we want to solve, our original problem was this, right? This is not solvable. I have relaxed this problem, okay? And this is quite a general routine, right? You start with a problem formulation, and in most of the case, the original problem is not solvable. So what do? You do some approximation. But in that approximation, you have to be taking care that approximation is not too vague. It should not be the case that I wanted to reach Everest, but I will just come to Kathmandu and say I have reached Everest. At least you should go to Everest base camp, right? So your approximation should not be too vague. You should be quite meaningful. Right? So in this case, we have also done some kind of a background that, okay, this approximation is not vague. This is not exactly solving that problem, but it is somehow doing something meaningfully, right? But now this is nice. This is a solvable problem. This is an objective function. This objective function is not convex. Not convex because of this part is convex, this part is not convex, this part is not convex. But constraints are fine. Constraints are easy to deal with. But now see, we have two variables, x tilde and C. What I will do now, I will be doing alternate minimization. Alternate minimization means what? Ideally, the problem needs to be solved for x tilde and C jointly. But solving it jointly is difficult to deal with. So what I will do, I will first solve for x tilde, fix C, and then solve for C, fix x tilde. This will make things easier for us. Why it will be easier for us? If I will solve for just x tilde fixing C, then that problem will become convex in x tilde. Next, if I will solve for C fixing x tilde, then that problem becomes convex with respect to C. So with a jointly it's not convex, but individually it is convex. So alternate minimization is a way to go forward. So what we have done, we did again some kind of a second layer of approximation, meaningful approximation. Fine, solve for C, solve for x tilde. Solve for C, solve for x tilde, and do till you converge. And what you do for the convergence, you satisfy KKT guarantee. So given theta and x, this is a nice simple optimization based routine where you can specify what level of coarsening you want to do, and it will give you the coarsen graph. So far, so good. We will also talk about the guarantees. But you can choose the level of coarsening. You can actually do from 1 million to 10. We have tried it. We have compressed 10 million size graph to 10. We have compressed 100,000 to 200, and there are of course trade-offs between the accuracy, the downstream performance, and the coarsening. That is there, but you can actually choose the level of coarsening, whatever you wanted to do. Okay. Now let's do certain guarantees. Right. So far we have sold you a good dream that you can do graph coarsening meaningfully. Right. Now what is the dream? See, what is the original data? X and theta was the original thing given to you, right? X theta is what? Trace. So let me define you something. So far any query here till now? How we reached till this point? No? Okay. Okay, see. For this data, theta and x is for this graph, and theta c and x tilde is for this graph. For this graph, there is a thing which we compute, which is theta norm. Theta norm is nothing but trace of x transpose theta x, and this is exactly the Dirichlet energy. Okay, so norm of x with respect to theta is quantifying the smoothness of this graph, and norm of x tilde with respect to theta c is quantifying the smoothness of this graph. Okay, what only thing in our control so far is the smoothness. What we have said, we are working for homophily graph, right? And we have a homophily graph, then smoothness is what we can actually looking for, right? So this work gives you the guarantee that whatever smoothness was there on the original graph, the data and the feature and the Laplacian matrix, the smoothness of the coarsened graph would be epsilon bounded. Epsilon bounded means it will be in the region of the plus minus epsilon ball. Right? Previous work we have not put any bound on the epsilon, but because this is an optimization based routine, there is a tighter bound on epsilon. So now epsilon is between 0 to 1. So just take away message is that this coarsening is also giving you a kind of a guarantee that whatever property of the data you started with, similar property is also pushed down into the coarsened graph. Okay. 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 Now see, we will not get into the proof part, but one if you want to work something here, right? Again, we have brought down epsilon any positive to 0 to 1, but this is also quite open. So far, we have not utilized any specific property of graph structure, but the moment you have different properties of graph structure inside the whole framework, right? For example, if you have a modular graph, you have a you can say like the modular and many different types of graph which have nice structure. This can still be brought down to lesser values. So the next problem anyone can work on is that utilizing specific graph structural properties to bring this bound lower. So this work appeared, our work appeared in ICML 2023 and Journal of Machine Learning Research in 2024. And JMLR is a quite elongated version, around 60-65 pages work. We have talked in quite detail about how to do it, but there are many open problems again. So far you can just see we have only talked about homophily type of a graph, but homophily is just a very small example of it. There are many types of graph structures there, right? Okay. What we have used it for, right? First, one of the simple use cases, using this method for scaling graph neural network. How scaling graph neural network? One of the biggest challenge in graph neural network training is what? Like building graph neural network is what? Training, right? So what if there is a mechanism where you have a graph, you compress it, right? And then train on the smaller graph. Train on the smaller graph, and whatever model you have trained is useful for the original graph. Got the context, right? Start with a graph. It is difficult to deal with it for training, so you compress it and train on the compressed graph. Whatever model you have learned, now use it on the original graph, right? So scaling, you have directly approached the scaling, and we have approached the scaling for both kind of a problem, for the node level problem and the graph level problem. And the justification is, even if you suppose you need to build a recommendation system, right? Maybe Netflix builds to use a recommendation system. Even if you are using the whole graph, in order to learn the embedding for a particular node, you have never used the entire propagation, right? You have never used the entire structure. You have always, most of the cases, you have used 2 or 3 layer of propagations, and 2 and 3 layer of propagation means 2 hop, 3 hop, or 4 hop, or 5 hop neighbors, not more than that. So even if originally if you will be using the entire graph for training, then also you have never used the entire graph structure for a particular node. You have only used the neighborhood. So the thing is, if you are able to do coarsening, which is meaningful, simply means from the practical setting, coarsening should preserve the neighborhood structure. It should not distort the neighborhood structure. So if you have done coarsening such that the neighborhood structure is preserved, it means that whatever you wanted to do node level wise or edge level wise on the original graph can be done on the coarsened graph. Okay. Then there are some other works just from the some extensions. I will skip it in respect of time. Let's see about again. Let's talk about the convex problem or not. Now we have a different version of the coarsening matrix, coarsening optimization problem. Can someone just quickly check and say whether this is a convex function or not? Convex optimization problem or not? Someone here attempted earlier, right? Whether it's a convex function or not? The title suggests it is, right? But just look at the loss function and say whether it is convex or not. Just for your help. This is convex. This objective is convex. Our variables are what? C and x tilde. So this objective is convex. This is convex. This is convex or not? This is convex this time, right? Earlier the mapping was what? X is equal to C x tilde. So C and x tilde were both together. In this approximation, C and x tilde are not together, so it's not coupled. So this becomes convex. So just a side result that, but this is not in approximation wise. This is not a good approximation. Just to make the problem convex, we have formulated it. So it was quite fast, and for a larger coarsening ratio, it was doing good, right? So even if it was a convex approximation, it's an optimization problem was convex. The results were not as good as the earlier one. So the answer was, this is not a very good approximation of the original problem. We will skip the details why it's not a good approximation. But many times, your approximation final result depends on the quality of approximation. So many times, even if the non-convex problems are quite good, it's not the case that if your problems are non-convex and the other contemporary problems are convex, so convex would be a better way. It's not always the case. Okay, move. Now the next extension. So far what we have done, just to wrap up, we have graph, we have features, and we wanted to coarsen it. Okay. Now what we have also labels. You know what is labels? Means you also know the certain class information of the nodes. Okay. And now I want to extend the framework of coarsening for the labeled graph. Okay. So one way to use directly is use the deep learning training, which people have used now. There are recent works where they do the gradient matching, but there are restrictions for it. In a sense, the first restriction is, if you are already able to train on original graph and force the gradient to a new graph that you are learning, then you are able to deal with the larger graph. So then what's the purpose of coarsening? You are defeating the purpose of coarsening at the first place, right? Next, well, in the whole way, you are using a specific training, right? A specific loss function, specific training. So it becomes quite dependent, a kind of a particular task dependent, but does not become too generalizable. That is one issue. But now what we want to do, we don't want to get to a deep learning based training for now. Just come with a simple routine which can be optimization based and also use label information. So can you suggest how you can use label in the existing setting? So just one hint. Suppose C is a mapping, what we have done so far, and Y is the each label, each of the labels, right? I define a new matrix, that is C transpose Y, known as the profile matrix. So profile matrix would be nothing but the quotient size dimension the label. So suppose in this case what we have 2, 5. So it will be 5 cross 3, 5 super nodes and 3 labels. So phi matrix will indicate what? In each super node, how many nodes of each class have been mapped. So 2, 1, 0 means in the first super node, 2 number of class 1 label is mapped, 1 number of class 0 class 2 label is mapped, 1, 1, 0, 1. Right? So this phi will denote this. Now just tell me, if you want to do graph coarsening with label information, you would like this kind of a quotient graph or this kind of a quotient graph? Below 1? So how you will define mathematically that you need to have a below 1 kind of a thing, not the top one? Just look at the phi matrix.
We want to reduce the dimensionality of phi from R P N to R E prime.
Yes?
We have less number of things, but everything has the same.
See, now you only focus on phi. Whatever we have done, the way to reduce the dimension, have the same explanation. Now I want to look at the label, right? Just the label. So the dimension wise, they have the same. I have reduced from whatever, 8 to 5 only. So both the cases are mapping from 8 to 5. Now I am talking about the quality of graph coarsening. Quality, you are saying that this is better than this, but how you will put it down mathematically? Just look at the phi matrix. So if the rows are, if all the row values have some number, that is a good thing, or only one of the entry have a high number? Only one of the entry have high number. So in a sense, what I am trying to communicate to you is, right, you break down problems sequentially and then you identify what you want. So from this part, what we understood is that if I want to learn C, I should be learning C such that the corresponding phi that it will generate should have sparser rows. And sparsity is in my control, right? Sparsity is a well-defined thing. Abstracting out what we can do finally, right? So the moment you have identified phi matrices, now with these two examples, I want to say I want to learn that phi for which this is sparser, simply. And that is your problem now. So what we will do now, I will be doing graph coarsening, extending the optimization based routine such that now I have two variables also. Phi, I will bring an additional variable which is phi, and will force what? Phi needs to be row sparse. The moment I will say phi is row sparse and I can provide certain guarantees to it, then I am directly saying that there is a very less number of mix-ups. There could be better ways also, but what I have done is a smaller way. What my group has done is this way. So I want to enforce sparsity over row, and this you can do. So many people also argue, right, कि if you will, how can use label information without going with the deep learning mechanism? Sometimes in this case it was easy to deal with, but many cases it is not easy to deal with. And one of the success of deep learning or neural network based thing is that they are able to use label information quite well than the non-neural network based architecture. Other non-neural network based architecture has faced a lot of difficulty on using the label information directly, right? So fine, okay. So what we do, we need an extra regularizer onto the FGC or the graph coarsening mechanism that we have developed before, And there the goal is we will be enforcing sparsity, row sparsity. In this case, two different mechanisms we tried. One was you directly optimize this regularizer, very naive one, and another is that you use entropy, row-wise entropy. So if row-wise entropy, you will minimize the row-wise entropy. That is also indirectly doing the same thing. If you have one mass concentrated for one entry of a row, then it will have less entropy, right? So you also minimize the row-wise entropy. And this is what is the next set of things. Let's not get into the more details of it. And there are certain theoretical guarantees that one can get with these routines, certain guarantees that the reconstruction error would be less, the cut guarantees are improved, ignore, you will invert it back and then identify the effective resistance, those would be also reduced. So we'll completely ignore those details now. We'll happy to discuss if you are if you are interested into it. Okay, let's do finally few more algorithms. Okay, again carrying forward the coarsening thing, okay, the compression thing. Now what is my goal? I have this graph and I want to coarsen it. While coarsening, I have also this requirement that my graph, coarsen graph, should have specific structure. Structure means I want to have either sparsity, bipartiteness, multi-component, and tree. There are different ways, right? Now, I will not talk the formulation here. The thing simply what I want to explain is that the moment you have for one kind of a problem a very well principled optimization based routine, it helps you in extending it easily to other contexts, right? So in this case, for a structure, you can see this is not changing. This is quite the same what we have started with. But because it was a principled and optimization based thing, it was easy to deal with new extensions. So in this case, the structural thing is quite difficult to deal with, but before someone has already established that if you really want to learn graph with structures, one of the easier way to use the spectral properties. Spectral properties, why so? Because for many of the combinatorial properties of a graph, for many, not all, and many useful properties of a combinatorial properties of a graph structure can be encoded through the eigenvalue properties of the graph matrices. For example, for a graph, if a graph have 3 components, okay, then the 3 number of eigenvalues for that graph Laplacian would be 0. So it is exactly encoding the combinatorial property into the eigenvalue property. Dealing with combinatorial property is NP hard, but dealing with eigenvalue properties are analytical. You can actually solve for it, right? So the moment you mapped the combinatorial requirement as an analytical eigenvalue requirement, you are able to solve for it. So this is what one can do. So if you want to enforce structure while coarsening, you utilize the eigenvalue type of regularizations. Fine. Some other applications also what we have done. Apart from deep learning training, one of my group have also used the graph coarsening for epidemiological parameter estimation. So epidemiological parameter estimation is what you want to study the you can say the epidemics, for example COVID, right? And you want to model it, you really need to be quite fast when there is an outbreak, right? And dealing with a population size graph is quite difficult. So there what they tried, they compressed the graph, the population graph, studied on the smaller graph, and then extrapolated the idea to the larger graph, and they were doing quite well with this kind of approaches. Okay, just because we have a lot of undergraduate students, I will also talk about one problem statement, which was primarily carried by UG students at IIT Delhi, and that appeared in TMLR, Transactional Machine Learning Research, last year. No, I think this year, last year. We have entered into a new year, right, 2026, yeah. So what they did, it was a class project. They attended the optimization class and they extended this project. So they identified that coarsening is quite good, but cannot do quite well for some specific type of data sets. So they brought in the idea of modularity, right? So what they clubbed the graph coarsening thing with modularity, solve the problem, and solution was not just solving it with optimization based. They also brought some new maths for these problems where they provided the guarantees that this loss function with modularity are actually satisfying both strong and weak consistency suitable for clustering. Second, they also extended this loss function to utilizing for a deep learning training. So far I have been saying it's a completely optimization thing, but the loss function was quite good. Say they did some variational autoencoder, they use it in the variational autoencoder training, and they come up with a very nice clustering algorithm. Okay, just so in a sense, it's not research is not only that only you need to do masters and PhD to do research. Many times, many good researchers are also being carried by the energy of undergraduates. So feel free to carry any of the research frontier. You will be able to do quite well here. Okay, I have some time. Let's talk next. Okay, so we're still carrying the discussion of coarsening only, right? It's quite active. The third frontier is, how many of you have heard of federated learning? Okay, quite well. So federated learning is that paradigm, right, where data sets are situated at different clients, okay, and without sharing the data sets directly, you are able to train a model. So how you train a model? There are different ways, right? Suppose, and clients could be anything. Client could be like, each person can be one client, bank can be one client, hospitals can be one client. There are different privacy rules also where data sharing is not allowed. But in order to build a good model, what you need? You need to have as large amount of data sets as possible. But different regulations are restricting you to not share the data sets. So how do you deal with it? The central framework of federated learning is like this. You train your model locally, the other client will train their model locally, and you share the models. There are more details also of what way you can share the models, what way you cannot share the models, but the big picture is that you share the models directly, right? And then you train. But in those cases also, just sharing the models also sometimes expose the vulnerabilities in your data, and many times there needs to be many checks while sharing the models also. What we are trying to convince here is that for the graph based data sets, you can have two layers of privacy and two layers of mechanism to ensure the privacy on the data sets. How? Firstly, when you coarsen the graph, right? So suppose each node is what? Is a client. Each node is a client, and the sensitive features of each node are the feature x1. The moment I am compressing it, what I am doing? I am putting a set of nodes together and then aggregating the features. So we are concealing sensitive information. One can have a more detailed way to deal with it and put more constraints. So coarsening can be a very effective way of doing privacy preserving, you can say privacy preserving data sharing arrangement, right? So this is what we are trying to prove. When we do privacy like mechanism, there are certain things that we need to prove. For example, differential privacy. Differential privacy means if one data is differential private to other data, they need to satisfy certain assumptions, certain theoretical properties. Those things we are just doing it, but some results are already there. But one other thing which is quite unexplored at a greater context is that whatever DP mechanism, whatever the sensitivity mechanisms have been studied for the Euclidean data sets have not been well studied for the graph data sets. How so? So when we talk about the neighborhood, for example, if I am talking about two different data sets, right? How they do? They remove one entry and then see how is my performance changing. In graph data set, removing that entry is not well defined. Removing entry means the moment you remove node, certain edges will be removed, right? If you removed edges, certain things will. So the privacy part for graph is not well defined, and that could be one of the problem if you're really looking for a research area to work on. So privacy mechanism for graph data is one such thing. So in this case, what we do, you have a graph, primarily dealing with the graph data. You compress it, right? Compress it, apply whatever DP mechanism you want to apply. Not apply also, it's fine. Then you have two layers of things. In one way, you share the model. There are also studies provided that sometimes sharing the model is not always welcoming in terms what they say. It is not always facilitating in the overall learning of the environment. Right? So you need to also share the data. But sharing the data was too tricky. But with this mechanism, you can actually share the quotient graph. And there is impossibility theorem also. If I share a quotient graph, for example, if you're an attacker, right? If I shared you a quotient graph, do you think you will be able to regain the original graph in whatever way? No. So suppose in the quotienting mechanism I shared with you theta c and xc, and I do not say anything to you. Do you think you will be able to recover theta? No, not at all, right? You will never be able to recover theta. Even if I say the what is the original size, then also there will be loss of resolution. You will not be exactly able to recover on what data it was trained. So quotienting can facilitate you the sharing of the private data directly. So this is an ongoing activity. Certain guarantees we have established. We have not published it yet, but yeah. Okay, so I think there are enough of graph quotienting. Let's shift the gear to something else, and I will be open to questions if you have. Then we will move to the robustness aspect of graph neural network. Any quick question on graph quotienting or graph compression? Yes.
Why are your methods better than diff-pull type methods?
Why are my methods better than diff-pull?
Yes.
I have not said it here, but the simple comparison is that it's an optimization based routine and there is guarantee on the quality of approximation. So those methods do not provide guarantee on the quality of approximation. That is one reason. Second thing is that they have a deep learning based thing, so they become very subjective. In some of the use cases, they could outperform our method, but if you take their method and also take this method and apply for a variety of application domains, then it is more likely that this method will perform better, because it is not based on specific way to learn the graph quotient. It is a simple optimization based routine.
So instead of optimizing, instead of formulating as a convex or non-convex optimization problem, if we extend that for a loss function, that is what I believe diff-pull does. In diff-pull, you learn a
Yes.
matrix that you learn C matrix using a basic loss function, not as well defined and well thought out as yours, but having some primary features from there.
Yes.
Since we are not we are doing a gradient descent across that, I believe there are parallels there and here. So how are where
So-
is
So the most critical part where it completely distinguishes this one is this particular result, the epsilon similarity result. That is not available there. This gives you the guarantee of approximation, right?
okay.
So just gradient based approximation will not give you this guarantee. Right? You have to have the structure from the properties that we have enforced. So if they are able to do it, I have not gone through the paper in detail. If they are able to provide the epsilon solution, it is as similar as their method. There is not much of a difference. Huh.
The FCC approximation
Huh.
is effectively not too dissimilar if I would have defined a loss function in a similar manner, differentiably, then your FCC would effectively become gradient, right?
It's here also we are using gradient, but there is a second. We are also learning the features there. They are not learning relearning the features in between. They are only learning the mapping, coarsening, right? So when you will see this
The features are then transformed.
transformed directly, they are not they are not part of the optimization problem. So it is like a you can say two disjoint processes.
Yes, got it.
That's because we have a joint optimization problem. It gives you the guarantee of a descent and also satisfying the epsilon similarity. Okay, fine. You have a question? Yeah, please.
Why the modal plan between instead of modal plan
In federated learning, why? I'm just giving one example. In this case, one can share model parameters. Sharing model means model parameters, right? There is no other way to share models. Sharing model parameters and sharing model, it's the same thing. But I am also arguing that you can also share the data, the course and data, and still guarantee that the privacy mechanisms are taken care of. How does what happen? Can you?
Concealing the graph data.
Coarsening the graph data.
You mentioned
Concealing the information. See, so that is what I've said. Suppose earlier, for example, we can take your case. So suppose you are a node and your features are sensitive features. You are connected to maybe 10 nodes, 10 other nodes. The moment I am coarsening, I am putting maybe 10 similar nodes put together, and features are the aggregation of it. So your individual sensitive features are now removed. You have a local aggregation. So that is one way where I am saying that the sensitive attribute corresponding to one particular node is somehow being shared with much less resolution. So we are taken care of. Furthermore, one can also work on making a specific optimization routine to deal with not only just the aggregation, you can come up with some other layer of transformation of the feature. So in a sense, you aggregate, learn a quotient feature, and then do some transformation. So as the downstream task is not affected, and still your sensitive features are not shared.
Okay, then will that hurt accuracy with the global model?
So there are trade-offs. There are trade-offs, and one needs to work on that part. How we can deal with without sacrificing the accuracy. So it will affect the accuracy. But in a sense, one other experiments what I did, once you shared the quotient graph, and another way we did the DP mechanism. So in order to achieve the same level of privacy, right, the DP, the noise we wanted to add were much higher, and it was worsening the performance. So in this case, we have both the results. In some cases, the coarsening was actually very effective in privacy mechanism and also in the accuracy. But in some applications, it was the reverse. So if you are interested in it, you could look into this kind of a work. Not much has been done. There is no one explicit answer for your question. In some cases, it was better. In some cases, it was not better. Okay. Thank you. So if there are no more questions, we'll switch the gear and let's talk about something more. Okay. So now what we will talk about, we have understood how to reduce the size of the graph, right? Reduce the size of the problem. The moment I am reducing the size of the graph, I am just reducing everything associated with it, right? I am reducing the resources associated to deal with that graph, right? I am also reducing the memory associated to store that graph. I am reducing a lot more things with there. Now I will switch the gear to a different kind of a problem. The different kind of a problem is adversarial robustness for graph machine learning. So adversarial robustness is that you have a clean graph, okay, ideally, and the graph that you have to deal with now may have noisy edges and noisy features, or both. Okay. Attack could be of different types. There could be meta attack, there could be targeted attack, there could be random attack. So at the end, what I am saying, instead of having a clean graph, clean data, I have a noisy data. Okay, and there are studies which says that how the performance deteriorates fastly. It's a perturbation rate versus the accuracy, right? So this curve is for the meta attack. Meta attack means you have attacked it with a target individual nodes. Individual nodes means you have changed the features, or you have added extra edges to that particular node. So accuracy deteriorates much faster when you have the targeted attack and different types of attacks. So let's see. What are different types of attacks? One can modify the node features. One can add or delete edges. One can also add or delete nodes. Okay. So what is our goal? Our goal is this, right? It's simply saying that ideally we should have received data set which is X. Okay. And on that X, if I would have received that X, I could have built a model which is theta. And for that theta, I would have received this guarantee. Now the question is, I do not have access to clean graph, that is X, or data. I have an access to X plus delta. So can one come up with a mechanism that whatever we wanted to do with X can be done on X plus delta? Of course, there are certain constraints on the delta. Not any arbitrary amount of delta you add to the data will still make this thing possible, right? There are certain limitations to it. So the limitations is also or natural, right? Suppose if this was your original graph, right? And if you attack every node randomly, right? And if you add too many edges, then those kind of attack would be quite visible, right? You will get to know in advance. You will get to know in advance that my data is already spoofed, right? Spoofed, or there is some issue with this. You will not do with it. So attack also needs to be intelligent, that it do not change the distribution of the data. If it changes too much, then it will be filtered out immediately in the primary study. So the delta budget on the attack is also justified. So, okay, let's see. Furthermore, there are again two types of attacks, two different types of attacks. One is the poisoning attack, and another is the evasion attack. Poisoning attack is you attack the data before training. So your training data is noisy. Okay, your training data itself is noisy. Second evasion attack is what? The test data that you will be dealing with would be noisy. Okay. So this is also a very well studied area. It's not. It's unlike coarsening. It's not new. It's not less studied area. This is well studied area, and this has been studied in quite a great context for regular deep learning. Right. It's for graph also. It is quite well studied. But there were certain issues which were not taken care quite well, and that we try to take care of. So at the end, any kind of a learning, any kind of a model learning thing is nothing but function learning. You all agree? Deep learning, machine learning, any kind of a learning is nothing but a functional learning, right? You learn a mapping function. So you have X and Y, you have a list of X's and Y's, right? Based on these evidences, historical examples, you need to learn that function, which for a new X new gives you a new Y new. It's at the end, deep learning, AI is anything related to this is nothing but function learning, right? So now there is a context in robustness part is that I cannot use blackboard. No? Okay. So see, if you have learned a function, right? If you have learned a function which maps X to Y, right? So there's an embedding I'm talking, right? You are learning a function. So deep model gives you what? It provides you embedding of particular data, right? So suppose you have for X the embedding is E, or for X1 the embedding is E1, and now what I have provided that the new data there is a noise in that data. So we have X1 plus delta, and for this if I need to learn the embedding, the new embedding that is the X1 plus delta, the embedding of X1 plus delta should not be too far from the embedding of just X1, right? This is what my requirement is. Otherwise what will happen? With a very small amount of change in my input data, the embedding would be very much different, and that is what we do not want. That is the core essence of robustness. Robustness simply says that if there was a small amount of change in your data, the change in the embedding should not be too much. If you are able to restrict the change in the embedding, then you have ensured robustness. Okay, so robustness part is clear. This is quite central in also able to understand the bias part and the fairness part of it. Okay. So robustness part is so far clear, right? If x was the input data, I map to y or e. If x plus delta is now a new data, a delta is not too big, then the E2, that the embedding that we will be learning, should be close to E1 that we want. There is, I will also relate it with the issue of biasness and fairness. So when we say the model is biased, right? When we say the model is biased, it simply means what? And let's take example of male, female, right? If I am a credit card company, okay, and I am using your features to predict whether you should be given credit card or not, right? It's a very lame example, but it's a quite good example. So if there is a male, I have all the entries, for example, education, salary, last job, where he's staying, where he's not staying, all these things. And something similar also for female. Only thing will change what? The female, the gender attribute. Only thing will change what? The gender attribute. For one, the gender is male, and for one, the gender is female. Whatever way you have encoded, it depends on it. Now, for an n-dimensional data, just for only one feature, you for one model is recommending for male yes and for female no. Right? There are explanations that why they are doing it, because historically they have not seen many women holding credit cards, so they have kind of carrying the momentum of the memory. But if you want to quantify from the mathematical part, for x case, right, suppose x and y are only differing in what? One attribute. So if you will compute the Euclidean distance or any distance between x and y, it will not be much. So the input distance, the domain, this side domain distance of x and y is very less, but the embedding output is quite different. So fairness is also related to the robustness aspect. So in a sense, if you want your model to be fairer, you do not want that model to be too sensitive for one particular attribute. Right? So this can be translated. Okay. So mathematically, there is a concept that if there is a mapping f from domain x to domain y, x1 and x2 are features, x and y are features in this case, and the map embedding is what? F of x and f of y. So if distance between the input is x and y is dx, and distance between the output embedding is d of fx and df of y, then if this distance is related to this distance by this property, then those are Lipschitz functions. Those are Lipschitz functions, right? And there is a quest that you learn a function with good Lipschitz property. What kind of separation you will have depend on the constant value L. Too large will be too random, right? Too large would be, in a sense, too much curvature. Very small L would be like a very plain straight line. You need to have a balance between the kind of depth that you want to have in your function. Okay. So the context what I want to motivate to you is that many issues, again the three different phases of ML, data collection, data model training, and deployment. First and third are mostly not in our control for the engineers, right? For those who develop. Only thing which is in our control is what? The second phase, the model training. And how we can take care of fairness and biasness issue in our limited role of a model training is from the understanding the function well, right? And this is what I am trying to communicate. Okay. So what we want, there is a Lipschitz function, and we need to take care of this Lipschitz property well in order to talk about the kind of a guarantee that can be say about the robustness. Robustness and fairness are related, right? If your model is robust, you can also extrapolate it to your model to be fairer. People have approached it, and we are also doing it, right? So put together, it is saying that embedding distance would be upper bounded by L into the input distance between x and y. If function is differentiable, then this also translates to the idea of the gradient would be bounded. Gradient of the function would be bounded. So for us and for all of us, all models are nothing but these functions, right? You all agree with this? You all are on the same page, right? Models are nothing but the functions that we want to learn. So there is something called certified robustness. So ellipsis guarantee and certified robustness. Certified robustness simply tries to map this delta and this L. Delta is what? Originally your data was x, and now instead of x what we have? X plus delta. What we want? Whatever output we were getting on x, I should be getting on x plus delta. So this you will be able to get till you satisfy this property. So it says what? In order to satisfy this property, it is saying that delta should be upper bounded by c by L, and c depends on the some constant of the function and L. So in terms of the ellipsis, what it is saying? The lower the ellipsis value, the better would be your robustness against change in the feature. But if you will make the L very low, suppose you make the L1 or just a linear line, then it is not, so the you can say the generalizability or the expressiveness of the model would be constrained, right? So this says that you should be having L as low as possible, but putting L very low is also not a good thing, right? So you need to have a good value of L, low as possible, but also be expressive as enough. Okay, so just some context of it. This is a clean graph, okay? X is the feature of this graph, A is the matrix, A and X is the clean graph, okay? Now instead of having the clean graph, I have noise added to graph matrix and noise added to the feature. So what I have access to? I have access to perturbation in feature, and I have access to the perturbed matrix. So you are only having A plus noise. This you do not know. You only have this, and you only have this. Okay. So you have the noisy access to the data, and this is one of the result. It simply says what? I want to learn a model. Okay. I want to learn a model A, f theta, and I have it's a L layer, and the activation functions are L ellipses, and norm budget simply means that the noise that being added to feature is E epsilon, and noise being added to feature is S. So what it is saying, suppose this is a function, okay, that you have learned on the clean graph, and this is a function that you have learned on the noisy graph. The distance between these two things, so this is the embedding of the clean embedding, and this is a noisy embedding. So the distance between the clean embedding and noisy embedding would be upper bounded by some constants. These constants depend on the budget of noise for the adjacency matrix, budget of noise for the feature matrix, into the norm, the product norm. Okay. This product norm is also well studied. Okay. So now see, the conclusion from here is, you do what you want. You want this value to be as small as possible. You don't want this to be grow too big, right? And this is upper bounded by this quantity. So you want to decrease as this as possible. You want to learn theta. So theta is your variable, right? It's not the case that it is given to you. So what people have, so in a sense, if this is not in your control, the budget and noises are already added to you. Only thing is in your control is what? This thing. So now you want to learn the model weights such that this value is reduced. This value is reduced. Okay. How you can do it? Can someone explain? So how you can learn the weights, model weights, such that the product of the model weights are as low as possible? People have approached it some initial starting point where, in a sense, heuristic. There are other very heuristic ways also. Can you think of a heuristic way? In a sense that you train your model, you get the theta, and later you do something such that the norms are not there. Regularized, yeah, you regularized, good. So one of the way people have also done what you learn without any constraint, and after learning you just normalize the theta. At the end you normalize the theta, so what you will get? You will get the product of the norm theta would be just 1. So in that case it will be L, the ellipsis value would be just 1. But again it will be reducing the expressive power of the graph. So accuracy and all have reduced a lot. Okay. Okay. Okay, fine. So let me say how we want to solve this problem. So how much time I have, Francis? How much time I have?
You have to stop soon, I'm afraid.
5-6 minutes, right? Okay, fine. I will just quickly wrap it up. Okay, so the problem goal becomes what? You got the motivation, right? Problem goal becomes now, I have noisy graph. From noisy graph, firstly, I need to learn a clean graph, okay? And on that clean graph, I need to learn the parameter model theta such that the gradient norm of function is less than some quantity, okay? And it will be flexible enough, okay? So it's difficult to solve the problem directly. There are motivations. So let's come to the point how we have solved it. So this is what the proposition that one can solve. You have a GNN training loss function, denoising loss function for the adjacency matrix, and denoising function for the feature, and you add this as a regularizer, right? Log of, say, product theta you wanted to minimize, and product theta is what your the layer weights. So you said what? I want to minimize this using this as a regularizer, okay? So this first was the formulation relating with the ellipsis thing, and then when you will solve it, this whole thing will also guarantee that this product will minimize. So this will further do what? This will guarantee that the L is also minimized, but this is adaptive, not a hard projection. Okay, now everything will become to ellipsis 1. Okay, fine. Let's come back and then short story closer. Solve this problem using optimization routine. Let's just skip that part. I just wanted to show you the results. So there are results here after solving this. Okay. One thing here is the accuracy, and here is the ellipsis bound. Okay. The relation between the ellipsis bound and the accuracy I wanted to map. If you have a very high ellipsis constant, in that case also, if you will not use any regularizer and solve, at the end you will have a very high ellipsis value. In that case also the accuracy was bad. And if you have a very small ellipsis value, just normalize the weight to 1, you have ellipsis value 1. In that case also the accuracy was bad. So the optimal accuracy level was coming to be for this thing. For see, this is ADALIP. This has the best accuracy, right? 77 and more, and the ellipsis value is around 5 range. See this. The ellipsis value is between 5, is around 5. The highest ellipsis value were around 20, and lowest ellipsis value is 1, right? So there exists a fine balance of ellipsis, and that we wanted to uncover through these experiments. Okay, so I think with this I will close it. There are other works also on the distillation part, but with respect to time, and if you have any questions, I will stop it. I will be happy to discuss further over tea, any question that you may have. Thank you.